You hold two small magnets above the table, turning them slowly between your fingers. They feel ordinary, cool, solid, almost weightless. You bring them closer. At first, nothing seems unusual. Then, just before they touch, you feel something change. The magnets pull toward each other and snap together with a tiny click. There is no string between them, no moving gear, nothing you can see reaching across the space separating your hands. You pull them apart and turn one around, bring them together again. This time, you feel the opposite. The magnets resist. You move one closer, and an invisible push seems to grow stronger. You can feel it through your fingertips, even though there is nothing visible between the two pieces of material. Turn one magnet again, and the behavior changes. You've probably done this before, maybe as a child, maybe with a refrigerator magnet, a small compass, a toolbox, or something sitting in a kitchen drawer. It is such a familiar experience that your brain barely registers it anymore. But stop for a moment. There is something deeply strange about what just happened. Two ordinary objects interacted across empty space, without touching, without wires, and without any visible mechanism connecting them. You can measure the force. You can predict it. Engineers use it every day, yet none of that tells you what you actually experienced. You saw a magnet move. You felt a force. But what was traveling through the space between your hands? And why should one orientation pull while another pushes? That is where the ordinary magnet becomes something much more interesting. Once you stop accepting the word magnetism as an explanation and ask what magnetism actually is, the simple answer starts falling apart. And that is precisely the kind of ordinary mystery worth examining closely. You do not need a laboratory to begin. The object in your hand is already enough. The deeper you look, the stranger it becomes, because the answer does not begin with two magnets. It begins much farther down, with the structure of matter itself. That is where we begin. That is where the ordinary magnet becomes something much more difficult to ignore. You can feel the force, you can watch the movement, and you can predict what will happen. But one question remains. What is actually pushing or pulling across that empty space? You may have been told that opposite poles attract and like poles repel. That description is useful. It tells you what to expect, but it does not tell you why it happens. Saying that a magnet wants to stick is not an explanation either. A magnet does not want anything. It has no intention, no preference, no little mechanism inside deciding which direction to move. Perhaps the answer is the magnetic field. That sounds more scientific, and it is. But notice what happens when you use those words. You have not really closed the question. You have simply moved it one step deeper. What is a magnetic field? Why does it exist? Why does a particular piece of matter produce one? And why does another piece of matter respond to it? Here is what makes this especially interesting. You do not need a physics laboratory to begin finding the answer. The mystery is already sitting somewhere around you. It may be attached to your refrigerator, resting in a toolbox, hidden inside a speaker, or tucked away in a child's old toy. The object is ordinary. The physics is not. Most people learn what magnets do long before anyone explains why they do it. You learn the words north and south, attraction and repulsion, and eventually the explanation feels complete. But those words describe the surface of the phenomenon, not its deepest structure. To understand that structure, we have to follow a trail that begins with something more familiar than a magnet: electric charge. From there, the path becomes increasingly strange. Charge leads to motion. Motion leads to electromagnetism. Electromagnetism leads us toward relativity. Then, unexpectedly, the story reaches inside the atom, where quantum mechanics and the behavior of electrons become essential. Before we go any deeper, though, there is a problem with the way magnetism is usually explained, and it has very little to do with the magnet itself. That last question matters, because magnetism has acquired an unfortunate reputation for being more mysterious than it really is. You have probably seen explanations online that talk about magnetic energy, vibrations, frequencies, or invisible forces that sound scientific but never explain what is happening. I find that kind of explanation frustrating because the real physics is already fascinating enough. Magnetism is not a phenomenon that science simply throws its hands up over. We can calculate magnetic fields, build electric motors, design medical imaging systems, guide charged particles, and predict how magnetic materials will behave. The mathematics works remarkably well. But there is an important distinction here. Being able to predict something is not the same as being able to picture it intuitively. You can know exactly what a magnetic field will do without having a satisfying everyday image of what a field actually is. You can use equations to calculate a force while still asking what those equations are telling you about reality. That distinction is important when we bring Richard Feynman into the conversation. Feynman's strength was not making difficult physics sound mysterious. It was almost the opposite. He kept asking what the words really meant. If an explanation sounded impressive but did not clarify the mechanism underneath, he kept digging. And that is the approach we need here. The version you may encounter online says that magnets possess some mysterious energy or frequency that makes them attract or repel. It sounds intriguing, but it gives you nowhere to go. What produces that energy? What determines its direction? Why does changing the orientation of a magnet change the force? The scientific version begins somewhere much more concrete. Electromagnetic fields, electric charge, moving charge, and the quantum properties of matter. That answer is less mystical, but far more interesting. Because once you follow the mechanism, you discover something simplified explanations leave out. Magnetism is tied to electricity. Electricity and magnetism are tied together by relativity. And the magnetic behavior of matter takes you inside the atom, where electrons obey rules that do not resemble familiar objects at all. You were not wrong to find magnets mysterious. You were simply given the surface of the explanation. And the deeper you go, the more surprising the real explanation becomes. So rather than decorate the mystery with mystical language, let's do what Feynman would insist on doing. Take the phenomenon apart and ask what each layer is actually doing. That is the kind of question this channel is built around. Not simply telling you what happens, but following the mechanism until the explanation actually makes sense. If you enjoy explanations that do not stop at, "that is just how it works," consider staying with this channel. The goal here is to take familiar things you have seen your entire life and uncover the science quietly operating underneath them. Because sometimes, the most interesting discoveries are not hidden in distant galaxies or complicated laboratories. They are sitting on your table, inside your home, or already in your hands. And the magnet is a perfect example. To understand why it behaves the way it does, we have to resist the temptation to begin with the magnet itself. We need to go back to something even more basic, something that seems completely separate at first: electric charge. Once we understand that, the strange connection between electricity and magnetism begins to emerge. That is where the trail begins. Electric charge is one of the basic properties of matter, and charged particles produce electric fields, which describe how electric influence is distributed through space. You cannot see an electric field, but you can measure its effects. A charged object can push or pull another charged object without physical contact. Already, the word field asks us to rethink empty space. The space around a charge is not merely nothing. It can be described by a quantity that tells you what electrical influence would exist at each location. You can think of the field as a map, but not merely a map on paper. At every point around the charge, the field gives a precise description of the influence that another charge would experience there. This idea becomes especially useful once charges begin moving, because the pattern of influence can change and propagate through space. In other words, the field is not just a convenient label attached after the fact. It is part of the framework physicists use to describe what is physically measurable. Once you accept that, the jump from electricity to magnetism becomes less mysterious, but not less remarkable. The invisible space between objects has become part of the story itself. Then something changes. The charge moves. An electric current is organized motion of electric charge. Run current through a wire, and a magnetic field appears around it. Place a compass nearby, and its needle can turn. The wire has not touched the compass. Something about the moving charge has changed the physical situation around it. This is the first major reveal. Electricity and magnetism are not separate forces that happen to coexist. They are deeply connected aspects of electromagnetism. And here is where the story takes a turn that would have delighted Feynman. Imagine looking at charged particles from different states of motion. The electric and magnetic descriptions do not remain completely separate. Under the mathematics of special relativity, electric and magnetic fields transform into one another. What one observer describes partly as an electric effect, another moving observer can describe as a combination of electric and magnetic effects. That does not mean magnetism is simply electricity caused by relativity. That slogan is too crude. The deeper point is that electricity and magnetism are woven together into one relativistic electromagnetic field, and the way you separate the two depends partly on your motion. Magnetism is connected to space-time. But we still have not explained the permanent magnet sitting on your refrigerator. For that, we have to go inside matter. A permanent magnet is not simply a tiny battery with microscopic wires carrying an ordinary current. Its magnetic behavior comes from the properties of electrons, including their electric charge, angular momentum, and intrinsic magnetic moment. The word spin can be misleading here. An electron is not a tiny classical ball literally spinning around an axis like a planet. Spin is an intrinsic quantum property built into the electron itself. And that matters because quantum mechanics changes the story again. Electrons occupy allowed quantum states, and their magnetic moments can interact with one another. In many materials, those magnetic contributions largely cancel. But in ferromagnetic materials, interactions between neighboring atoms can favor particular alignments of their magnetic moments. You can picture magnetic domains as regions where many microscopic magnetic moments point in related directions. It is a useful picture, as long as you remember that the real quantum description is more subtle than a collection of tiny arrows physically lining up. When many of these microscopic contributions cooperate, a material can develop a substantial magnetic field. The numbers involved are extraordinary. The elementary charge is only about 1.602 times 10 to the minus 19 coulombs, while the electron has a mass of about 9.109 times 10 to the minus 31 kilograms. Its intrinsic spin is 1/2, and its magnetic moment is naturally measured using the Bohr magneton, about 9.274 times 10 to the minus 24 joules per Tesla. Even the Earth has a magnetic field, typically somewhere around 25 to 65 microteslas, depending on where you are. Modern laboratory magnets can produce fields of many teslas, vastly stronger than the field surrounding us naturally. Yet the most important number may be one you already know: the speed of light. Exactly 299,792,458 meters per second. That constant sits at the heart of the relativistic framework connecting electric and magnetic fields. And you are already surrounded by this electromagnetic world. Your radio, phone, speakers, electrical wiring, and even the light entering your eyes all belong to the same broad electromagnetic framework. The magnet is not an isolated curiosity. It is one visible doorway into a much larger theory. Now consider what your simple refrigerator magnet represents. Its behavior reaches from electric charge to electromagnetic fields, from relativity to electron properties, from quantum mechanics to collective behavior inside matter. And there is one final step. A permanent magnet has to do more than become magnetized. It has to remain magnetized. In certain materials, the microscopic arrangement of magnetic moments can settle into energetically favorable configurations, while the material structure creates barriers that make reversing those configurations difficult. That is why the magnet can continue producing a magnetic field without burning fuel or consuming electricity every second. What looked like two pieces of material pulling across a table is actually the visible end of a chain that reaches astonishingly deep into physics. But there is a problem. After hearing all of this, it is still very easy to fall back on the familiar picture of two mysterious poles reaching toward each other. And that picture creates a surprisingly persistent misunderstanding. Suddenly, the magnet is no longer an isolated object. It is a small window into fundamental reality. That is the deeper picture. But there is still one familiar idea that can quietly pull you back toward the old explanation: North and South poles. You were probably taught that a magnet has a north pole and a south pole, and that opposite poles attract while like poles repel. As a description, that is perfectly useful. It helps you predict what a magnet will do. But description is not the same thing as explanation. Electric charge gives us a useful comparison. Positive and negative electric charges can exist separately. You can have an isolated positive charge or an isolated negative charge. Magnetic polarity does not behave in quite the same way. Imagine taking an ordinary bar magnet and somehow dividing it into two smaller pieces. You might expect one piece to become a north pole and the other to become a south pole. That is not what happens. Each smaller magnet still has its own north and south ends. Divide it again, and the same basic pattern remains. You have not uncovered a lonely magnetic north hiding inside the original material. You have created smaller magnetic systems with their own polarity. And this is where the common picture starts to crack. The phrase "opposite poles attract" tells you what happens. It does not tell you why. It is a little like saying that objects fall because gravity pulls them downward. True, but incomplete. The interesting physics begins when you ask what creates the field, how that field is structured, and how matter responds to it. The version most people have heard is simple. North pulls on south, and south pulls on north. The deeper version is more revealing. A magnet's macroscopic field arises from microscopic electromagnetic and quantum properties of matter, and that field interacts with magnetic moments in another object. You do not need to throw away the words north and south. They remain useful in everyday daily life, but you should stop treating them as the final explanation. That small distinction changes the way you see the entire phenomenon. The magnet is not a mysterious object containing two invisible substances called north and south. It is a physical system whose microscopic properties produce a measurable electromagnetic field. And once you see that, another question becomes unavoidable. If magnetism is not simply a force between two mysterious poles, why has that explanation remained so convincing for so long? That question takes us to a belief many people carry without realizing it. Magnetism is simply one of those strange forces that science never completely figured out. It is an understandable belief. Magnetic fields are invisible, and the quantum behavior underneath permanent magnets is far removed from everyday experience. Your senses were never designed to intuitively understand quantum fields. But there is an important distinction. Early scientists naturally described magnets using poles, forces, and attraction because those ideas accurately described what they could observe. The language was useful. The problem came later, when a useful description began to sound like a complete explanation. North attracts south tells you what happens. It does not tell you what creates the magnetic behavior in the first place. The version most people have heard is that magnets possess mysterious north and south poles. What modern physics reveals is considerably deeper. Electromagnetic fields arise from charged particles and their motion, while the magnetic properties of matter are tied to quantum mechanics, electron spin, orbital angular momentum, and interactions among electrons and atoms. James Clerk Maxwell's electromagnetic theory gave physicists a remarkably powerful mathematical framework for describing electric and magnetic fields. Later, quantum electrodynamics took the description deeper, treating electromagnetic interactions within quantum field theory. The Feynman lectures on physics are valuable for precisely this reason. They repeatedly encourage you to separate the words we use to describe nature from the deeper physical structure those words represent. And Nernst's extraordinarily precise measurements of physical constants remind you of something else. This is not vague speculation. The electromagnetic framework produces predictions that can be tested with astonishing precision. Yet you do not have to choose between two extremes. Magnetism is not completely mysterious, but it is not completely intuitive either. That middle ground is where the honest science lives. You can calculate what a magnetic field will do with extraordinary accuracy, while still finding the quantum description profoundly strange. That is not a failure of physics. It is a reminder that reality does not have to behave the way our everyday intuition expects. And once you understand that, the ordinary magnet in your hand becomes more interesting, not less. Because now you can actually see several layers of fundamental physics operating at once. You can now take this understanding out of the explanation and test some of it with objects you may already have at home. You do not need sophisticated equipment. In fact, the simplicity is part of the point. Take two small magnets and hold them about 5 to 10 centimeters apart. Slowly bring them closer. Notice the force as their orientation changes. Rotate one magnet 180 degrees and repeat the experiment. The attraction or repulsion can change dramatically, giving you a direct demonstration that orientation matters. If you have a small compass, place it several centimeters from the magnet. Move the compass around different sides of the magnet and watch the needle change direction. The compass is not seeing the magnetic field. Its own magnetic moment is responding to the field at its location. You can also place thin, non-magnetic materials between the magnet and a small ferromagnetic object. The interaction can continue through many ordinary materials, reminding you that physical contact is not required for magnetic effects. There is another useful experiment you should only perform as a thought experiment. Imagine cutting a bar magnet in half. You might expect one half to become north and the other south. Instead, each piece would have its own north and south ends. You have not separated two independent magnetic charges. These simple observations turn your home into a small physics laboratory. More importantly, they let you revisit something familiar with a completely different understanding. There is no need to force a dramatic conclusion. Just notice what the magnet is telling you. Each movement is a small demonstration of principles that connect your tabletop experiment to electromagnetism, quantum mechanics, and the behavior of matter at scales you cannot see. And that is perhaps the most valuable part. You can repeat these observations whenever curiosity returns, because the underlying physics does not disappear when you stop watching. You are no longer merely memorizing that magnets attract or repel. You are learning to recognize the evidence yourself. And that habit of looking closely is exactly how ordinary experiences become scientific questions. For a moment, let that idea settle. The same invisible interaction remains present whether you are experimenting deliberately or simply reaching for a magnet in an ordinary room. Now go back to the first moment, the instant when two ordinary magnets seem to pull together for no visible reason. Think back to that moment when you held two magnets above the table. At first, they were simply objects that pulled or pushed each other. Now you can see something much deeper. Matter, electrons, quantum properties, magnetic moments, electromagnetic fields, and finally, the force you can feel in your fingertips. Nothing about the magnet changed. Your understanding did. And every time you pick one up tomorrow, next month, or 365 days from now, that ordinary object can remind you that reality is operating on layers your senses cannot directly see. The mystery was never that science had no answer. The mystery was how much was hiding inside something so familiar. And perhaps that is the real lesson Feynman leaves us with. The most interesting mysteries are often hiding inside the things we stopped looking at. If this kind of explanation is useful to you, consider staying. That is what this channel is built around. Taking ordinary things you have seen your entire life and asking the deeper question, what is really happening underneath?